if you want, you can also remove this line, and then we have predicted the probability distributions for the entire class label. And as you can see, we have one line, extra line over here. We call forward using this input. So the network gives us some output, which we override the input and we then call softmax with the output. So it converts it into probability distribution. And we simply return this distribution. You could also return the scores if you wish, but probably, but make more sense. So this is why we are returning the probability. So these are the mostly used in visualization. This is more understanding what we are doing it, right? Okay, now this is the final function that we need to discuss before we get into the meat of the lecture, where we actually see how to train the network. So this is the update function. The update function takes in the parameter velocity, then the parameters of the network, the gradients with respect to each of these parameters, and it has these two other hyperparameters, which is the learning rate and the momentum term. So how much weight to give it to the momentum term? Currently, it is initialized with some default values. And so learning rate, we have set it to 0.01 and momentum to 0.9. And we can also change this, and we all want to do is we have to get best values for this. We will see how to find that. And now velocity initially is empty, and then we then set velocity. Now velocity will initially be all zeros. So when you do that, it will be all zeros, and we simply set it to a negative step of the gradient. So we have the gradients. So okay, we take a small step. So the learning rate size step in the negative direction of the gradients, right? So gradients will be the slope, but we want to go in the negative direction of the gradient so that we get to a minima. Right, so this is what we got, and this is what we call velocity. And then we update our parameters with the velocity. Next time, we do with this velocity. So this velocity will have some value. The velocity will have the values which is a small step in the negative direction of the gradient. With the momentum, what we are doing is we are saying, okay, do not forget which direction we are going in. Remember a little bit, but then update that direction with the current gradients. So we don't want to like completely go in a zigzag way. It may so happen that the current gradients are in the direction, the next gradients are in that direction. What the momentum term does, this is okay if you are going in this direction, it forces you to keep it over there because we have a high mu there. So this mu is 0.9, right? So 0.9 will depend on the previous step or the cumulative previous steps, and 0.1 will depend on the current gradients. Right, and this is what the current step will look like, and then we will take a step in the direction of the velocity. So again, it is a very simple function. This is what we are doing with the update. And you have seen all this theoretically, but we are just doing it in terms of code. And in the 4 lines, the stochastic gradient descent with the momentum. It sounds difficult, but you can see how easy it is to implement it. And in practice, even not, we use packages like Keras, but it is very useful to know what's going on under the hood. All right, so now we define a function which give us the mini batches. So both the images of the data point and the corresponding label. So here we are converting our entire training into mini batches, and then we return all the mini batches. So we take the training set, we take all the training labels. So this is the entire training set. Features or the images. So 60,000 into. So we can call it with the training set, or suppose we call it with the training set, it says 60,000 into 784. This is just 60,000, and mini batch size is again a hyperparameter, but suppose we set it to 200, right? So what we can then, what does it? So what we want to do is we want to shuffle it. We want to shuffle, and that is why we want to shuffle it. Why? Because we don't want the inputs, and when we, because of this shuffling, we get this name stochastic in gradient descent. And why do we want to shuffle it? So MNIST is a nice data set where it is already shuffled. So when we visualized it, we saw that, right? But suppose it was all fives, all fours, all zeros, all ones, and if you don't shuffle the data set, then what is wrong? What would happen? What would happen is that our gradients will be highly correlated. So our network, so what would the gradient descent do now? It will tell our network to first go in the direction of 5. So it will only teach us how to understand 5, how to recognize 5. Then it will teach you to understand 4. But by now it is forgotten what 5 looks like. Right, so it will not work for everything but the last data set type, right? So this is not good practice. So the first thing that we do is we shuffle the entire data set. It is very easy in Python. We simply call it permutation with a data set which is 60,000. So we got a 60,000 long list. We use it to permute the data set and the corresponding labels. Obviously we have to permute the labels in the same way. We permuted the data set so that we have the correspondence between the data point and the corresponding label. And then we loop over the data set. And then n is the size of the data set. If we are using training, it would be 60,000, and we loop over it with the steps of mini batch size with steps of say 200, and we create batch, right? So this is a batch because we say, okay, go from 0 to 200. It will be 60,000 and we loop over it with steps of mini batch size, right? With the steps of say 200, and we create batch, right? So this is a batch because we say, okay, go from 0 to 200. Right, so as we go from 0 to, so we take steps of 200 and put it in X batch, take steps of 200 and put it into Y batch, and then we do this, and then put this tuple, put this tuple of X batch and Y batch into mini batches, right here. So what will mini batches have finally? How many tuples it will have? Tuples equal to the size of the set, which is 60,000 or 10,000 divided by the size of a mini batch size, right? So 60,000 divided by 200. So this will have 60,000 by 200 tuples. So now we have all the mini batches that we want, right? So we can simply loop over our training set or test set in mini batches. So we call the first element of this mini batch we get. If we take the first element of this list, it will give us one mini batch with the data and its labels. Okay, so far it is good. So we are done with everything for the main function where we now use all this. Now, how we do use all this? We define a function. So this is the training loop, and it takes net, which is the model. It takes the training images, it takes the data set. So the training data set, the test, the training labels. So you can call this, it takes in the various things, and we will call it later. So it takes the training images, the training labels, the mini batch size, which are hyperparameter, the number of epochs to run our training for. So the number of epochs means how many times. So one epoch, look at the data set one. So we have 60,000 images, and if we have to say 3,000 batches, then if we go over 3,000 batches once, then we call it one epoch. Then we have the learning rate, which is hyperparameter, the momentum term, which is another hyperparameter, and then we can also pass it. So the validation images, the validation labels, this is a lambda, which is again a hyperparameter, which we will see how to get a good value for this. So this is the lambda in front of the regularizer, in front of the L2 regularizer on the weights, and this is a verbosity. This is simply how much we want to print. Okay, so these are the inputs to the loop, right? To the training loop. So we create an empty set validation loss for every epoch we create. We call this mini batch function with the training set. We call the mini batch function with the test set or the validation set, and we get mini batches for the training set and mini batches for the validation set. So far, so good. We are set. We have everything that we need. Now we run a loop for the number of epochs we want to run. Suppose we want to run it for 10 epochs. So we go from 1 to 10. For each epoch, we monitor the loss for every batch. So suppose we had 3,000 mini batches in the data set. So if we had 60,000 images, 200 per batch, maybe we have 3,000 batches. So for each of this batch, we will monitor the loss. Similarly, we will monitor the loss for every batch of the validation set. And the velocity we have seen earlier will initially be this empty list and will then get initialized to something once we call our update function. So then we loop overall, right? So once we do that, we will loop overall the parameters in the network, right? And for each parameter in the network, we append it to the velocity. And then we also loop over the mini batches, right? So this is where the actual training happens. So now first, what we do the training. We loop over the training batches for each batch. We do a train step. So remember, the train step does the bunch of things. It does the forward, then backward of the loss function. And what it does not do is updating the parameters. So remember the train step. It does the forward of a network, it does the forward of the loss function, it does the backward of the loss function, and it also does backward of the network. Backward of the network needs backward, which the loss function gives as. So we also do a train step and we monitor the loss. So we also do a train step and we monitor the loss. So for this batch, whatever loss we got, we save it here. And then we call update. So we had initialized our velocity with the zeros. So I said that velocity has to be zeros initially. So zero, mean it will be of the same size as parameter. Okay, so we have our parameter which is shaped. We have the velocity which is shaped as parameters, but it is initially all zeros, and then we call the we update the velocity with the parameters here, and the learning rate which we have passed into this function, and the momentum term which was a term which was again passed. We then so this now training. So this is actually changing these parameters. So after these steps, this would have changed. Okay, so the next is validation. So here we do not train, we simply monitor the value of the loss. So we loop over each batch in the validation set, and we do train step. But the thing to realize is we are not doing update because we don't want to use the test or the validation set to update our parameters. So we want to see, this is a holdout set. We want to see after training with my training set. Because this is the proxy for the real world. So if it works well on this holdout test set, maybe we can deploy it in the real world. Okay, so we then monitor the loss. We get this validation loss and we put it in the validation loss batch list. So we append this list with the validation loss, right? So we have done so far everything whatever is required in the beginning stage, but here we want to now check a few things. So we want to check the accuracy. So this is what we again define a few things, and then for each of the thing we have again the mini batches stuff. So here we are doing nothing but simply predicting. We want to simply say, okay, what the network will give us for this input. So we could have also used this mini batches, right? We have also used these mini batches, but we are doing this manually. So we got a batch here. So we are looping over. We are taking a big step of mini batch size. So we go from 0 to 6,000 here, 0 to 10,000 here. Mini batch size, if it is 200, we go from 0 to 200, then 200 to 400 and so on until we reach 60,000. So we get 0 to 200 images here, 0 to 200 labels here. We put it into, so we simply put it into this thing, and then we call network.predict for this, and we get the predicted value of the network for this batch. And we get the predicted value of the network for this batch. Okay, and remember, prediction will actually give us the label. And then what we want to do this is we want to compare against our label. So what are the labels? Our labels are white trim. So like we have to check how well we are doing, right? And which we will do here, which we will do in check accuracy, right? We will be doing check accuracy, and similarly we will also get our final predictions on the validation set, and again we will compare this with the validation set ground truth. Okay, so in check accuracy, what we will see this function defined here. It simply checks, so we have the ground truth, we have the prediction. It simply checks if the ground truth is equal, I mean, it is correct or not. When we add 1 to the counter, else we don't add, and divide by the counter by the size of the set. Divide the counter by the size of the set. So suppose we have 60,000 and we got 50,000 correct. So then we divide 50,000 by 60,000. So we get 5 by 6. So we get, say, 80 something percentage as the accuracy. So this is all that we doing here. So we get the validation accuracy for this epoch. Okay, so we will be doing this. We also monitor the loss. Remember, we were saving our loss for every batch. We will then say, okay, what is the loss for the entire set? We simply need to average it out. So we need to divide it by the size of this. So this will be the training loss. This will be the validation loss for every epoch. So if we monitor it, we have to monitor it, and okay, so we switch this verbosity on, then we can print everything so that we have collected so far. So the mean loss, the training accuracy, which I feel essentially which epoch is it, and how many epochs, and finally what we do is one of all these epochs get over, we return the network, and along with that we return the accuracy which we have achieved until we have done by doing several epochs. So we had kind of this, so we just walked over it so that we can continue with the babysitting part. Okay, so now suppose what we want to do is we want to invoke that we have created can remove this. Right, so now suppose what we want here is we want to invoke all that we have created until now. So we are using this anyways. We are not really going to use this one actually. So we are going to use train and test loop. Train and test loop takes in the number of iterations that we want to train it for, the learning rate that we want to use for that training, the lambda or the weight. So the lambda in front of the L2 regularizer, which is on the weights. So the lambda for the weight, decay, and verbosity. We set the learning rate to LR. We say the number of hidden nodes is 10. We say the number of output nodes is 10. So we have a 2-layer network. We go from 784 to this, right? And the learning rate is a hyperparameter, which comes from this function. And this is what happens over here. And here we then call and we create an object for the neural network class, and here we can see that 784 to 10. Okay, so here we actually have a single layer network. So we are not even using a 2-layer network because we want to see how we want to do babysitting. It takes a lot of time for it to run. So we have simply a single layer. So we have just one layer for this neural network. So it's a linear classifier. So we simply go from, so we never really use the hidden nodes. So we never really use the out, or we never really as the output node. So we will have essentially one linear classifier, and then we simply pass this neural network into our residue function into our training loop. So that's about the training, but it also gives us the trained model. So we call our training loop with a model. So this is the this is what we have seen till now, right? And the training labels, mini batch size, we have set to 1,000. So if we have the 60,000 training images and if our mini batch size is 1,000, then we will have 60,000 and 1,000. So we will have 60 batches, right? So we have 60 batches here. We decide how many epochs we want to train it for. So whatever we call it with so if we call it with 10, we call it train for 10 epochs, right? So we set the learning rate to we set the learning rate, and this is the validation set. This is the lambda in front of the L2 regularizer and the verbosity. And finally, we return the accuracy achieved using these hyperparameters. And so next, what are we going to do is we are going to call this, we are going to call this function, right? So how do we do that? Like, this is a big question, right? Like we don't know, should we use 100? Should we use 10? Like, should we use 0.1? Should we use, we do not know, right? So we are going to learn how to choose what is the correct learning rate, and similarly lambda. So we are going to learn how to use that, and I will also teach how to choose these two things. But the methodology is pretty generic. You can use the same methodology to choose the correct values for all the hyperparameters. Okay, so we have a function which takes in these three numbers. This is the number of this is the number of epochs, what the value of learning rate is, what the value of lambda is, and what it gives as finally the accuracy. What it gives finally is the accuracy on the validation set. And based on the validation set accuracy, we will choose what the good values for lambda and learning rate are. Okay. So as the very first step, what we want to do is we want to set the learning rate to something small, something like 0.00001. We will set the lambda to 0, and we will call our train and test loop. Right. So remember what the train and test loop takes. So where is our train? So what we have seen the train and test loop, right? So what it takes. So this is what we have to understand, right? So train and test loop function. Remember, we have seen the number of iterations. I just want to run it for one epoch, and my learning rate and my lambda are this, and verbosity is high. Verbosity is high, so verbosity is 2, and what I get as output is this, right? And so what it prints it, okay, the loss is this, and we can see the training accuracy over here. So the first sanity check is completed, and what do you think? To make it, to me, it makes sense, because our training accuracy is about it is around 9%, right? So a random distribution to give us at random. If I simply say I have to give you, so suppose I have 10,000 test set images, and for each of these I give you value at random. I would get it right maximum 10 times, right? So on an average 10 times, and I am getting 8% or 9%. And also, what do you think of this? So this loss you can see over here, right? This is around 4.56, because initially I would expect it something like something like all 0.1 10 times, so that it adds to 1, and negative log. If I find a negative log, I may be getting the value, right? So this is what we have to double check for the first iteration, is whether reasonable or not. So what happens if we do not disable the regularization? Then the value of our loss changes. So then we are not able to do the cross entropy loss. Okay, so we disable our regularization and then we check the sanity of our loss. It seems okay, the accuracy seems okay now, so we are happy and then we move forward. So this is the loss range, right? So we are happy and then we move forward. Yes, it is the correct. And what about the accuracy? Does it make sense for an untrained network? Because it is good as random. So let's know how to do the next step. Now let's crank up the lambda and check what it does to this lambda function, right? So we should get a huge loss, but it is not, it just goes from, actually previous case when I checked, it was around 8%. Now it is giving me 9% and the log loss is also around 4.56, right? So we have to think like whether is this log range, loss range correct, or is this good or not, right? So this is what I have to check it. So this is another sanity check. Now, this is the most important step, and this is what I advise you to start with, a very good sanity check. If your network is working at all, is to try and overfit it to a small subset of data, in this case 20 images. So what we do is we take the first 20 images of the training set and call it training set X train subset. So we take the first subset of the labels and call it Y train subset, and we set our X train and Y train with these subsets. So for sanity check, we simply print out the shapes and we get 20,784. Remember the training set, this initially was 60,784. So we will now deal with simply the subset. So a tip is that you make sure you can overfit to a very small portion of the training data. If you are not able to overfit to a very small portion of training data, there is something wrong. You should go back and look at some bugs which you can, there is some very basic bugs which need to be fixed before we can take the next step. So we set the learning rate to something small and turn the regularization off. We take the first 20 examples of MNIST, turn regularization off and use SGD. So we call our train and test loop for 10,000 iterations with a very small learning rate and 0 lambda. And you can see that the losses are slowly going down. That's what we can see, and the accuracy is increasing. So finally, you can see that 100% accuracy. And does this make sense? Yes, because we have only 20 images. So on these 20 images, our model is able to fit perfectly. So this is good news. But the bad news is that obviously it does not perform very well on the test set. It only gives us 47% accuracy on the test set. This is still good because MNIST is very easy data set, but usually your validation set accuracy would be even lower. But the good news is that we are able to fit it over here. This is very important step that you should do for debugging the network. So whenever you create a new network, what you have to do is you have to try to fit this network onto a very small portion of the training data. Here we have tried to fit our network onto 20 images and we have been successful. So we get a very small loss and we get a training accuracy of 100, which is awesome. So we are successful in overfitting. So since we are successful in overfitting, we go ahead and then to start with reload our data set using MNIS.load_data and simply essentially get to our original state. So there is nothing new here since we had nest with our data set here. Because we have made, right, we reload our data set. Now we know that our model has sanity, because the initial loss makes sense, the initial accuracy, okay. So a small portion of the data we have taken. The next step is to choose the correct values of learning rate and lambda. So let's start with a very small learning rate and a very small lambda, right? And so let's our learning rate to 1 e power minus 7, and also the lambda to be 1 e power minus 7, and let's call the training loop for 500 epochs with the learning rate these. Right, so what do we observe here? That the loss hardly goes down from 2.3 to 2.29 after every 500 epochs. And what is the inference over here? That probably the learning rate is too low, because we are taking tiny steps in the negative direction of the gradient. So we are hardly updating our weights. And since we are hardly updating our weights, we are not really learning. And the training improves from 13% to 14%. So yeah, this makes complete sense. So now let's try a larger learning rate. Let's say 1 e power 6. So we start with this thing, and we keep the lambda e power minus 7 and call the training and test loop 500 times. So as soon as we start, we get the loss to be not a number. Why do you think this is happening? Because our learning rate is so big, but the loss is completely exploding. It is taking such a big direction, such a big step with the gradients. That's going out of the floating point range. So the parameters here, so the parameters get to a stage, say 1,000 or a million, and then we compute the loss using these millions in the parameters, you get a very large number for loss. So we get a NaN. Now obviously is whatever we started with. So our loss is infinite, and our training accuracy is around 10%. So this is again cost is very high and high learning rate. And now, so whenever your loss is exploding, reduce your learning rate until your loss does not explode. So now what should we do? So now let's try a value between 1 e power minus 7 and 1 e power 6. So this should actually, because we did the e power 6, not e power 4. Okay. So let's choose our learning rate to be, say, e power 4. So this is a big number, but e power 4 still seems to do something, right? So we have our learning rate as e power 4 and lambda is e power minus 7. And then we train using these numbers, and then we got our loss function. Right here, this is what we got now. Right, so this 89% accuracy on the training set and 87% on the testing accuracy. Our loss is also down to 16. And note we have our lambda on. So initially we started with 2.3, but now since we have our lambda on, we will get a large number as loss. And now the sum of the cross entropy loss and the L2 regularization loss. But this means that the learning rate is still too high. Loss is not decreasing to very small numbers, and probably what we know that is that rough range of the learning rate we should have a somewhere between say 1 e power 4 and e power minus 7. So what we should do is, we should not do this manually. What we should do is, we should have a cross validation strategy for this. Where we will do, of course, is to find validation. We will see it in a minute. So first in the step, like, we should get a rough idea of which parameters work, so which ranges for this hyperparameters work. And in the second step, we will do longer experiments with the finer searches. So we will see what I mean by this shortly, and we should repeat this as necessary, as much as necessary. And a tip for detecting explosions in the solver is whenever the cost goes 3 times the original cost, we should break out early. So even with the regularization added, if the cost is more than 6 point, so we multiply 2.2 with 3.3, so we get 6.6. We should say okay. We should try different hyperparameters for that training. So now we will run 100 experiments. Right now we will run 100 experiments with different hyperparameters. So we will run a loop from 1 to 100. We will create a loop for different hyperparameter combinations. So we will create different learning rates. So we will choose a random learning rate between 10 to power 10 to the power minus 7. We put a power on 10 to the power minus 7 to 10 to the power 4, right? Similarly, we will get a random learning rate between 10 to the power minus 5 to 10 to the power 5. So we will get a random lambda between 10 to the power minus 5 to 10 to the power 5. And we will simply monitor the accuracy returned by our train and test loop. So we will use the learning rate, random learning rate, which we got from here. We will use the random lambda and we will monitor the value of the validation set accuracy here. And we will print this output. We will say that so for this iteration, for this validation, so we get this much validation accuracy using this learning rate and this lambda, right? So for the first try, we got this much validation and accuracy. And using this learning rate and this lambda from each iteration, when we run this, we get something like this. Okay, so here we are only showing 9. There are, say, a lot of these of 100 such numbers. What do we see over here? So basically, we are trying to understand that learning rate of 10 to the power minus 5 and lambda 0.00001. The best validation set accuracy is 83 percentage, right? That is what we could see over here. And finally, it is we get something nice over here, right? 92.33, and some cases it is no. You can look into each and every case. So when we use a learning rate of each case, it is getting, see, for each values of lambda, the accuracy is being checked. So when we use a learning rate of 0.001, we get a very low accuracy. So this gives us a hint that lambda should not be so high. So this definitely gives us a hint that lambda should not be high. So look at here what we got, a decent accuracy score over here, right? And here we have a learning rate of no, just you can look at a learning rate and a lambda, everything, and which is giving the accuracy, and you can figure out like which accuracy is really great. So we say that, okay, please remember this is something good that we are noticing. Yes, and let's also remember the other 90. So where else did we get some good numbers? We got some good numbers here and here, right? So one over here and the other over here and here, right? So this is what we are getting. Or you will have a better idea now. In this case, we know that our learning rate has to be 0.1 is good, 0.001 is good, and again 0.001 is good. So here we know that between 0.01 and 0.001, so this is 0.1, right? So 0.009 is 0.1. So 0.1 and 0.001. Between this is good. So this is a good information because now we have nailed it down for the small range. Also for the lambdas, we know that, okay, 0.002 is good. So we know that our lambda has to say between 0.002 and 2. When you run it, you get a better range, but we now know, okay, the learning rate has to be between 0.01 and 0.001. Right, and the lambda should be no, like this is how we are just trying to get the ranges. We say that our learning rate has to be between 10 to the power minus 1 and 10 to the power minus 5. Okay, and we also say that our lambda has to be between 10 to the power minus 5 and 10 to the power 2. We again run 10 of these experiments, and now let's see what we get. So let's now note down where we get some good numbers. So we see that we get, so the best validation accuracy, you can see over here, right? I think this is good and this is good, right? So these seem to be good. And the first one seems to be really bad, and this also seems to be bad. So if we do this, what we can learn, what we know about the hyperparameters. So the learning parameters are still fine, because with this range of learning rate, we have a with this range of learning rate, for example, with the 0.02, we get decent numbers. But with the lambda of with the lambda of this one, what is happening? So this is what we have to understand. For each lambda and learning rate, you can do the comparison and see whether it is good or bad, right? Uh, Learning rate of 0.005 is good, and right, that's what we sorry, learning rate 0.005, like how it looks like validation accuracy. So this is how you have to compare for all the cases, but you'll get a sense for where your hyperparameters lie. So the message here is that we know that, okay, if we use a learning rate of say 0.01 and lambda 0.01, we will get high accuracy. We will get about 92%. So if you want, you can then also run between several cases and see that, to check if it is between 0.02 and 0.05, because both of that give us high numbers. So we can then run the another experiment with a small range, right? We can also do say 2 or minus 3, 10 to power minus 3 to 10 to power minus 2. So you can run again and again for certain values for the experiment and get even better numbers. So in this case, we have only chosen the two hyperparameters, the learning rate and the weight decay. But in practice, you can use this strategy to find the correct values for all hyperparameters. So remember, do sanity checks, load the data set, visualize the data set. The very first step, do a sanity check. Visualize the data set. For the value of the loss function, it should something be meaningful. The validation accuracy should be something meaningful. Then you do a post to find search on the hyperparameter space, and we just saw how to do that. And if you do this, you will be able to find what is the correct hyperparameters for training your network, right? So I think this practical part is clear to you.